Welcome back to Principles Engineering. Today we're talking about free body diagrams as we continue to learn about statics. Before we get started, be sure that you've downloaded and opened your guided notes. You can use those either in the electronic form or the printed form. Either way, it'll help you to keep track of the information we go over in this presentation and give you a little more time to focus on what we're talking about versus trying to write everything down. The guided notes are given to you with presentation areas where you can record the information. Let's get started. So when we talk about a free body diagram, we're basically talking about a way of visually representing an object and the force interactions on that object. We use a simplified diagram of the object, and the individual objects are isolated from their environment, or what we call their system. And what we try and show is all of the external forces acting upon them. This lets us figure out how something can be in static equilibrium, this free body diagram, because we learned from our prior lesson that in order for an element to be in equilibrium, the forces have to balance. And these very simple diagrams, like this truss to the far left, we can simply add up our forces and our moments and calculate the requirements for it to be in static equilibrium. So we talk about a free body diagram, we've got to talk about some of the components that go into it. We've talked about the component itself or the element itself that we isolate, but the forces that act on that we can break down into a straight line push or pull, which is a vector quantity. Remember that vector quantity differs from a scalar in that it has direction and magnitude. The direction is always shown by the arrowhead. An example, the first arrow on the left-hand side is pointed up, meaning that the force is going up. Now I can think of that as either pulling from the bottom or pushing on an object. The force in the middle is going to the right, and the force on the far right-hand side is angled up at some angle theta. So remember that direction is shown by the arrowhead. Now the magnitude is represented by the relative length of the line segment, and that represents how hard you're pushing or pulling. For rotational efforts or twisting efforts, we talk about moments. And that occurs when a force is applied at some distance away from a rotation point. We indicate those with circle arrowheads that are pointing either CW clockwise or CCW counterclockwise. You may also hear counterclockwise referred to as anti-clockwise, the opposite of clockwise. So let's talk about moments here quick in review. Remember that a moment is equal to a force times a distance, and that distance has to be perpendicular to the line of action. So in this example, I've got a wrench on a bolt and a force applied at the end of the wrench. There's some distance from that point of rotation to the line of action or where I'm pulling or pushing with that force. That distance is the little d distance for the moment calculation. It's kind of important to remember that the shape of the wrench really doesn't matter. So if I put this zigzaggy wrench in there, I still am measuring a force times a distance. My force is applied at the end of the wrench, my point of rotation, and I measure perpendicular to the line of action to get my distance. It didn't matter the shape of the handle or the fact that I'm offset. It's perpendicular to the force. So let's look at even a wackier one and look at how the shape does not really impact the measurement. So here's a completely wacky handle. And in this instance, I'm going to apply 5 newtons at the end of the handle, which happens to wrap back around. And I measure from my point of rotation to the line of action the perpendicular distance, 1 meter. The moment is the distance times that perpendicular or force. So the force of 5 newtons times the perpendicular distance, sorry, I misspoke, of 1 meter, or 5 Newton meters. It really didn't matter the shape of the handle or how I got there. So when we draw a free body diagram, we're going to follow a little bit of a procedure here just to make it a little simpler as you start out. So consider this diagram. We've got 3 books stacked on top of a table. I have each book weighs 5 pounds. And we're going to draw a free body diagram of the top book. So the very first step would be to isolate the object and sketch that isolated object. When we talk about isolating an object, that's what references the free and the free body diagram. It's the object by itself. And simple geometric shapes are fine. In this instance, we're going to use a rectangle. So the isolated object is the top book, and it looks like a rectangle. The second step that I'm going to do in this process is I want to sketch the applied and normal forces. Now, those are terms you haven't heard yet, but we talk about whatever the object is in contact with and supported by the second object can be replaced by a normal force. So in other words, the red book is supported by the black book. That black book is providing a normal force. That normal force stops the top red book from falling. So I apply the weight of the book, that's an applied force, and the normal force, which is the reactionary force of the black book pushing up on the red book. Now, why are these two equal? They're equal because the book is not undergoing any acceleration. So now we label the object and the forces. Well, I told you the weight of the book was 5 pounds. So the normal force which pushes it up must also be 5 pounds. That's what defines that the book is static or not accelerating away. It comes from Newton's second law, which force is equal to mass times acceleration. There's no acceleration, thus there must be no net force. Now the last thing we're going to do here is we're going to label dimensions and put dimensions into our free body diagram that represent the dimensions of the actual object. Now, this book diagram doesn't really require any dimensioning, but the truss that's to the left does. We need to be able to calculate some angles. So that's what those dimensions allow us to do. We put in any lengths as well as angles on the diagram. So let's look at some practice problems here. So in your guided notes, you're going to find a sled. And this sled is made up of the sled itself and 2 kids sitting on top of it. That's what we're talking about as the sled. So I draw an equivalent object, just a simple geometric shape. In this instance, I chose a rectangle, or a square rather, that gray square. And now what I need to do is represent the weight. So the weight is both the weight of the sled as well as the weight of the kids on the sled going down. Notice that's a vector force. Now I know there's some friction in this system. So when I pull the sled, there is some resistance from the snow. So I'm going to put that in as friction, and that acts to decelerate the sled. That's what would make the sled stop if I pushed it and then let go. The normal force is the force that's stopping the sled from sinking in the snow. But you're going to notice that the normal force does not appear to be the same length as the weight. Well, what all that means is I've got an applied force on the string, and that applied force can be broken up into a component, the blue component, which is the opposite of the friction, and then the red component, which adds to the normal force to equal the weight. And there I have a free body diagram. Notice that I've labeled the diagram with the angle of the force coming from the string that's pulling it. Well, that wasn't so bad. So let's look at another one. This is a refrigerator. So we're going to isolate the refrigerator to be by itself. In that isolation, I'm just going to draw it as a square. Now notice that the square is at an angle, just like the refrigerator is at an angle. That'll help me to keep things straight. The weight acts straight down on the fridge, and it acts straight down on my square too. I've got a normal force from the ramp pushing up on the object, but I show it pulling up from the middle. Remember what we said. A pushing force up is the same as a pulling force up. It doesn't matter. So my normal force is supporting it, pulling up. And here's the force from the fella pushing. That's that applied force. Now again, I have some friction, a lot of friction in this instance, trying to keep the fridge from moving. And if I was to break my weight into components relative to my applied and frictional forces, or in line with the ramp, what I would see is I've got a red component that's going to be equal to the normal force, and I've got a blue component when added to the friction force, which is going to be equal to the applied force. And that's for the fridge not being accelerated up the ramp. So how about a pulley? This is a pretty useful way to represent a pulley because we can take this pulley system and we can isolate it. So let's start out and look at the free body diagram for mass 1. So we just bring mass 1 by itself. Again, a little gray square. And you're going to notice that now I've got the weight pulling down, and that's the weight of mass 1. Well, if that is not accelerating, I know the force normal, and we call that the force in tension, has to be equal to the weight of mass 1. That's an easy free body diagram. Well, let's look over at the movable pulley now. Now this movable pulley has an external force on it. So when I represent that by a circle, the first thing I'm going to draw is W2 plus the weight of the pulley. So what that means is the weight of mass 2 plus the weight of the pulley, both pulling down. Now I've got two strands supporting it, and they're split evenly in the forces. So I've got a force of tension on strand 1 and a force of tension on strand 2. If I added those two together, that would have to equal the weight of mass 2 plus the weight of the pulley. And remember that in this type of a system, the tension forces are equal throughout. We learned that in civil machines. So we have some reactions, and those are external force reactions to an element in its environment. And let's talk about some of the different types of support reactions. We'll go through these one at a time. When we talk about a cable, rope, or chain. Now that has a unique attribute. Cable, ropes, and chains can really only pull. We talk about a pin, and a pin, simply stated, is a example would be a bolt through a hole is a pin. Now the other free body diagram force we're going to see is a roller or a roller reaction. That is a support like a wheel on a surface. It only supports in one dimension. It will roll. And also what a cantilever looks like. We talked about cantilevers when we were talking about moments in our last lesson. So when we do the free body diagrams, we often put letters along with our forces, and that will help us identify both the location and the type of force. So let's look a little closer at the cable support. So a cable, rope, and a chain can only be in tension. You can't push a rope. So if I was to draw this weight being supported by a cable from the ceiling, my free body diagram of the weight would show the tension force in the cable and the object weight pulling down. That's a cable support. Now here's an example with two cables and a sign. If we look at this, the free body diagram of the sign and the cables, got cable A and cable B, I would have a label, tension force in A, tension force in B, and then the weight of the object along with the angle. A pin support is represented by this little triangle down here. And the little symbol here with the tick lines, that just means that it's grounded. So the pin is fixed to something permanent. So when I say there's a pin at point A, it just means that point A is supported by two directions, both lateral or back and forth X and up and down or Y forces. Kind of like a bolt through a hole. Now I talk about that force as the reactionary force at point A in the X direction. Similarly, I would talk about the vertical force as a reactionary force at point A, but now in the Y direction. So that type of labeling. So a pin is replaced with two reactionary forces, one vertical, one horizontal. A roller support can only support downward pressure. So its reactionary force is perpendicular to the surface. Perpendicular to the surface. I probably shouldn't say downward, because the roller is mounted on a vertical surface. It would then be a horizontal force. But it's one reaction force perpendicular to the surface. Again, this is the reactionary force at Y. At A in the Y direction. Notice the visual representation for that reactionary force of a roller is the grounded symbol and a circle. When we talk about a beam and a truss bridge, typically they're supported on one side with a pin and one side with a roller. We call this a simply supported object. So this is a simply supported beam. Now, if we're going to create the free body diagram for that, we'd start out with the beam itself, nothing more than a rectangle. On the middle of the beam, we'd put the load or the force acting down. On the left-hand side of the beam, we'd replace that pin with a reactionary force at point A in the X direction and a reactionary force at point A in the Y direction, because the pin supports both the X and the Y direction. And then we'd also put a reactionary force in B, but only in the Y direction, because that roller only supports a force perpendicular to the surface it's in contact with, which in this instance is Y. That's a simply supported beam. Well, what if I got something sticking out of a wall? We call that a cantilever. And the cantilever has to be replaced with two forces, a horizontal and a vertical, and one moment. So let's look at the free body diagram for the cantilever. First, I want to represent the beam sticking out, the cantilever beam. So I just sketch it. Add the force on the end. I know there's two forces at the junction with the wall. There's a reactionary force at point A in the X direction and a reactionary force at point A in the Y direction. And I also know that I get a moment. And that moment has to oppose the moment of the force out here. Now notice this force pushing down and assume this is pinned. It's going to make the cantilever beam want to rotate clockwise. So the moment at the joint has to be opposite of that clockwise rotation, hence the counterclockwise. Moment at point A, counterclockwise. So let's summarize these support reactions. We talked about when we contact something, we replace it with a normal force, just a simple support. My mouse sitting on the desk has a normal force supporting it. A cable, rope, or chain can only be a tension force, tension, pulling. A pin is replaced with two reactionary forces, one vertical, one horizontal. And a roller is replaced with a single reactionary force perpendicular to the surface. And last is the cantilever, replaced with a horizontal, a vertical, and a moment. So let's try and pull this all together and draw a free body diagram of this truss bridge. So look at the truss bridge for a moment, and on the left-hand side over here, at point A, you're going to see a pin. Point C has a roller. And then at point B, or node B, I've got a 500-pound weight. So let's start drawing this. You'll notice that the pin was replaced with that reactionary force at A in X, reactionary force at A in Y. The roller was replaced, the reactionary force at C in Y. And then my 500-pound weight was represented just by 500 pounds in the middle. Pretty easy. So when we talk about a free body diagram, remember our process. And this wraps up our presentation on free body diagrams. The first thing we're going to do is we're going to sketch an isolated object. We're going to isolate the object all by itself. Then we're going to sketch in forces, normal and applied forces. And we talk about supporting forces. Remember, we talked about those different classifications of supporting forces. Simple contact, cable, rope, chain, pin, roller, and a cantilever. Sketch those forces. The third step is to label all your forces. Remember our labeling method. We use the joint where it happens, so reactionary force is R at pin A sub A in the Y direction, sub Y, R A sub Y. And then we also want to label and dimension our free body diagram. Hopefully this gets you moving along and doing some free body diagrams, and we'll start an exercise where we practice this together. Thanks for watching.